Good morning. We're going to discuss ray paths in an inhomogeneous medium today. So far, we have discussed what we call as homogeneous mediums in the sense that whenever we looked at reflection or refraction, we really considered only a sharp interface in refractive index. For example, if we looked at refraction when we studied Snell's law, we sort of considered, say, one interface here, right? And we had different rays, right? N1 and N2. So this entire medium is made of one refractive index N1. This entire medium is made of another refractive index N2, and then you have a normal through the interface, right? And depending upon the refractive indices, right? So you could have, for example, a light ray come in this way, right? If it makes an angle theta 1 here, right, and it's going to make an angle theta 2 here, and then we know that from Snell's law n1 or over here, let's say this is theta 2, let's say this is theta 1, then n1 sine theta 1 is equal to n2 sine theta 2. But the important point here is that in this entire medium, it is the same refractive index n1. And same thing here, in this entire medium, the refractive index is same n2. So within each side of the interface, we have a constant refractive index, or all over that side, you have the same refractive index n1, for example, on one side, and n2 on the other side. Within the medium, we did not have any changes in refractive index. So now what we are going to look at is, for example, if I have material, or if I have, say, a case where the index of refraction is not constant, it is inhomogeneous, it is changing, then light would bend according to how the refractive index is changing, and that's what we are going to look at. One very well observed phenomena of observing things in an inhomogeneous medium. uh, you must have seen a mirage on a hot day somewhere, right? It may appear as if there is water on the road. That is because when, for example, if this is the road, right, this is hot, right? It is hotter here, and as you go up, it gets little cooler. So right on top of the surface of the road, it is very hot, right? And the density of air changes because of this hot and cold, and because of the density of change in the density of air, the refractive index also changes. So the refractive index here right on top of the road is not constant, right? It is if the air is less dense, right? So air near the ground has a higher temperature, right, than air much above the surface, because this is hot right here. Here you have higher temperature of air than up here, right? This is lower temperature. So because the density of air decreases, the refractive index increases, right, as you go above the ground. So as you keep going above the ground, here there is less air, and here there is going to be more air, right, because this is cooler, right? So in the cooler parts, the refractive index is going to be higher, the refractive index. Here it is going to be lower, the refractive index. So you're going from a lower to higher refractive index. So you have what we call as a gradient index. So because of the density of air is changing, because the road is very hot, it is less dense on top of the surface, the index of refraction is also lower. So if you have this gradient index, obviously the light will bend, and that's why when you are on the road, because the light rays coming in bend like this, bend like this, it appears as if there is a pool of water here, right? That's the mirage. So that's what we are going to discuss in more detail, how ray paths would be in an inhomogeneous medium, and of course we will be using mainly Snell's law to do that. So now let's consider an inhomogeneous medium. So if I have an inhomogeneous medium, to make it simple, what we will do is we will restrict ourselves to one particular case where the refractive index is changing continuously only along one direction. So the case that we are studying is the refractive index is changing along one direction. So unidirectional change. And then we are considering that it is changing continuously. Okay, so if I were to draw or visualize such a medium, right, I can approximate it to something like this. So I may have an inhomogeneous medium, so I can divide this inhomogeneous medium into several layers. Okay, so this is my inhomogeneous medium. So I could call, say, the refractive index in this part of the medium is N1, here it is N2, here it is N3, here it is N4, so on and so forth. So as you are going, for example, this could be something like the road example that we discussed. Right on top of the road, there is less density, so there is less refractive index, and as you go higher along this direction, the refractive index is changing. So that's a unidirectional continuously changing refractive index. And now what we are doing to make to analyze the situation, we are considering this inhomogeneous medium as if it is made up of very small, thin, infinitely thin layers that have, within each layer, the index of refraction is constant. So we are approximating a continuously changing index of refraction with several layers of constant refractive index from N1, N2, N3, N4, right? So now suppose your ray of light goes from this medium at an angle θ1, right? So it's going to go, let me change the colors here. So this is going to go, and when it is incident at the interface between N1 and N2, you know we have to use Snell's law. So we draw a principle here, normal here, and let's call this angle as phi 1, right? That's the angle of incidence because that's the angle with respect to the normal. So that ray is going to bend depending upon the refractive index N2, right? So let's say it goes this way, it bends this way, right? And let's call this angle the angle of refraction in N2 as phi 2 and this angle as theta 2. Okay, then this ray from N2 is going to be again incident on the interface between N2 and N3, and we can do the same thing again here. We draw a line here, right? And then basically what we are going to have is again the index of refraction is different in N3, so you're going to refract again, right? So again you would have the same thing. This angle would be angle of refraction. We will call this as phi 3, right, and call this angle as theta 3, and basically this goes on. So this goes here, again you draw a normal, right, and then again depending upon the refractive index it bends one particular way, so we can call this phi 4, that is the angle of refraction, and this is theta 4, right? So once again we are considering a ray of light that is in the first layer N1. It is starting out from N1 at an angle theta 1. This is not the angle of incidence. It is the ray at which the angle at which the ray of light is going from, say, an object, right? And that is incident at the interface between N1 and N2 with an angle of phi 1, and it gets refracted by phi 2. So now if I were to use Snell's law for the interface N1 and N2, then I could write N1 sine phi 1 is equal to N2 sine phi 2. right? Or I can write this as n1. I can leave the left hand side the same, and on the right hand side, instead of sine phi 2, I could write it as sine 90 minus theta 2. You see that this angle is, you see that this is a right angle, right? So if I want phi 2, which is this angle, I can write it as 90 minus theta 2, right? So that's what we did here, and you know that 90 minus sine 90 minus theta is cosine theta, right? And you can basically carry on this same thing, right? And you can also see that basically for the next one you can do the same thing, right? So if I take this triangle now, this would be my angle of incidence, right? So let's call this alpha for now. So this, if it is alpha, alpha plus theta 2 plus 90 degrees is 180 degrees in the triangle. So then I would have alpha would be 90 minus theta 2, or that is also phi 1, sorry, phi 2. So this angle alpha is also phi 2. So for the interface between n2 and n3, I could write the same thing, n2 sine phi 2, that is on this side, that's the angle of incidence, would be equal to n3 sine phi 3. But again, by applying the same logic, I can write sine phi 3 as sine 90 minus theta 3, or I would get that as n3 cosine theta 3, right? Now if I were to look at the first medium n1, then let us look at the angles in this particular triangle here, in this triangle. So in that triangle we would have theta 1 plus phi 1 plus 90 is equal to 180, right? Or I can write phi 1 as 90 minus theta 1, right? Or then I can write this n1 sine phi 1, right, as n1 sine 90 minus theta 1, or I can write that as n1 cosine theta 1. Similarly, we know that n2 sine phi 2 can be written as n2 cosine theta 2. So this is also n2 cosine theta 2. So you see what I am getting there, that n1 cosine theta 1 is equal to n2 cosine theta 2, and n2 cosine theta 2 is equal to n3 cosine theta 3, and it goes on so forth, right? We just used simple law of refraction starting from the beginning. So if you did not follow what I said or what we discussed here, I request you to rewind the video and go through the math again, right? So you can see how we are going between different slices of an inhomogeneous medium. We are approximating an inhomogeneous medium as if it's made up of several layers, wherein each layer has a constant refractive index. So here we considered 4 different layers, n1 to n4, and we started with a ray of light beginning from n1 at an angle theta 1 and is incident on the interface between n1 and n2 at an angle phi 1. And we started from here and we showed that basically n1 cosine theta 1 is equal to n2 cosine theta 2 is equal to n3 cosine theta 3, so on and so forth. Or basically what we could do is